I want to do is to take you to some time back. So let me introduce myself. I am Mangala Sunder. You have seen me as the coordinator of this project. So let me tell you a bit about theoretical chemistry. The large part of theoretical chemistry over the many years has been the development of quantum chemistry, computational chemistry, and so on. And the other fundamentally important component for theoretical chemistry is statistical mechanics and the molecular interpretation of thermodynamics. Thermodynamics is a macroscopic science. It's based on experiments, but the fundamental conclusions taken from thermodynamics are experimentally well-known conclusions. Therefore, when you propose theoretical models, you must make sure that you have taken the experimental considerations. And in that process, thermodynamics came up with something like three laws, I guess, essentially. The first law of thermodynamics being conservation of energy. And the second law of thermodynamics has to do with entropy and also spontaneity. And the third law of thermodynamics simply defined a zero scale for entropy and also that the absolute zero cannot be reached. That was the third law, which is very important. But these laws were known before one understood the molecular basis for these things. The molecular basis for thermodynamics was given many years ago, almost 170 years ago, by Ludwig Boltzmann. And you know Boltzmann's name from Maxwell-Boltzmann statistics and velocity distribution in physical chemistry you would have studied. Boltzmann is the father, one of the founding fathers of statistical mechanics, and also he believed in the molecular theory that the system is made up of atoms and molecules. He believed in that very strongly at a time when people were not very convinced about molecular models. So thermodynamics, he provided from the point of view of molecular motion, molecular kinetic energy, and velocities. He talked about thermal equilibrium, and he also proposed a very famous equation known as the Boltzmann transport equation for the evolution of molecules in space and time due to interactions among them. So Boltzmann is the father, and the mechanics was later taken up by Josiah Willard Gibbs. I'm sure you know the name. Gibbs was the other founding father of statistical mechanics. And the Gibbs method, called the ensemble method or very large collection of molecular systems and then calculating properties. So they provided the molecular basis for thermodynamics. At the same time, when quantum mechanics was being discovered in various forms, in various instances, we all go back to Max Planck as the founding father of quantum mechanics, because the black body radiation, which was a problem in 1900, understanding the radiation, the distribution of the radiation intensity as a function of the frequencies of the light radiation that came out. That distribution was a fundamental problem, and Max Planck solved it by saying that the black body has large number of molecular oscillators inside, and these oscillators emit energy not continuously in any frequency, but according to definite discrete frequencies, which were called the H. He gave that formula E is equal to H nu, where nu is the frequency of light, and h was a constant introduced by him. Using that discretization of energy, that is saying it's like currency for us. There's nothing below 1 paisa for us. There's nothing below 1 cent for an American. That's a minimum currency. So all transactions happen with that discrete quantities. So in that same sense, he said molecules transact energy with the external surroundings in discrete form, in packets. He did not say anything about light. The radiation that comes out of the black body, when you increase any body which doesn't decompose, if you increase the temperature, initially it will be light red by 600, 700 degrees. And then as you increase the temperature, it becomes red hot. And if it doesn't decompose or dissociate, if you increase the energy even further, it becomes white hot. By the time it reaches white hot, it's about something like 2000 degrees or so. Very, very high temperature. Obviously, the light that comes out of it comes off all frequencies. So how much light in one frequency, one other frequency, etc., if you have to study, this was done by what we call as the distribution of radiation. I'm not going to go through this. This lecture I can share with you, but the basic ideas. He said this is the distribution of the light that comes out. On the y-axis, you have the intensity of light, and on the x-axis, you have the frequency of light, wavelength of light. You can see that. So, wavelength being very small mean it's a light of very high frequency. Wavelength and frequency are inverses of each other. Therefore, you can see that the left-hand side of the graph is a very high frequency light, ultraviolet. The middle region is visible, and the far right, infrared and other radiation. So how do we get these graphs for different temperatures of the black body? So you can see at 3000 Kelvin, you have a graph which is at the bottom, and at 4000 Kelvin, you have a graph whose maximum, you can see that, whose maximum is slightly left of the maximum of 3000. In 3000 Kelvin, you don't see the maximum very well. But between 4000, 5000 and 6000, if you see it, the maximum is shifted towards higher frequencies. As you increase, the maximum radiation intensity and the frequency is shifted towards the left side. Nobody was able to understand this graph completely, and it was Max Planck who came up with the quantization hypothesis, and he derived the statistical mechanical law at that time. So this was quantum mechanics, birth 1900. Then all of you know that Albert Einstein, a little later, 5 years later, Albert Einstein studied the photoelectric effect. So there's a lot about Planck's distribution. I don't want to do this because my timeline is another 35 minutes and I must give you some overview. So you can see the photoelectric effect was studied by Einstein with, if you can ask one of the questions that we need to answer, A, what is photoelectric effect? B, what are the observations? C, what were the explanations then, which did not explain everything but some, but then how did Einstein come up with the answer? What is radically new about the proposition? You see that the next thing is very important. Einstein received the Nobel Prize for Physics in 1921 for his contribution to the understanding of photoelectric effect. He published 4 or 5 papers in the period 1905-1907, very significant research papers. And during that period, he was working in the Switzerland Patent Office as a clerk. So the analogy is that Ramanujan, being the clerical job in the Port Trust in Chennai, okay, building mathematics. Srinivasa Ramanujan, you can see some analogy. That's something to do with a job, and the rest of the time they are always thinking about the science and so on. So Einstein published this, and the Nobel Prize Committee did not know which of these three papers should we give the Nobel Prize for. They were discussing. And I think then the unanimity was that the experimentally photoelectric effect was very well known, and so they gave him the prize. But what is the photoelectric effect? At the end of the day, it is one line. What Einstein said was, light itself is not a continuous wave, but light of any frequency consists of a large number of packets. Okay? And these packets have energy given by the Max Planck formula h nu. The frequency of that light tells you what is the energy of the packet. So if a light is very intense, a lot of white light is falling, the intensity is very large, which means the number of packets per square centimeter per unit time, that number is very large. So Einstein redefined light as consisting of packets. The name photon for these packets was later given by a chemist. It was Gilbert Newton Lewis, G.N. Lewis, whom all of you know as the Lewis who contributed to chemical valence, the octet theory, and then bonding, chemical bonding and sharing of the electrons, unshared pair of electrons, and then unequal sharing of the electrons, and all these things. These were proposed by G.N. Lewis. Lewis, in around 1925 or 26, he gave the name photon to the light packets. It's a chemist who defined photons. Okay? It was Einstein, a physicist, who characterized the photons. But again, the point is quantization. Light itself consists of quanta of energy. Niels Bohr, I'm sure you all heard, the next person who used these ideas when he wanted to study the spectrum, the emission spectrum of hydrogen atom. Sorry. I will call him later. Supposed to have done that. I'll just switch off this. Okay. So Niels Bohr came up with a model for the hydrogen atom. Niels Bohr was working in the laboratory of Ernest Rutherford, and Rutherford had given the model of the atom based on the solar system that he was familiar with. He assumed that something similar to that the electrons move like the nucleus at the center, and the electrons are distributed like the solar system model. Before that, there was a Thomson who had what is called the plum pudding model. What he said was, its electrons are everywhere and they are spread around, and the mass of the atom is distributed all around like a cake, white cake. Plum pudding is something like that. So he defined, Niels Bohr came out of all of this and said, atoms, the electrons move in specific orbits. The angular momentum of the electron in those orbits has a unique value, and that is n times h by 2 pi, where h is a Planck's constant, and n is a number, 1, 2, 3, n cannot be 0. N is, as the electrons are moving around a point, there is always an angular momentum about that point, and the angular momentum has fixed values, which means the electrons are not moving anywhere within the volume, but on specific orbits separated from each other. And then he calculated the energies of these orbits, and he found out that the difference between the energies gave exactly, they reproduced the hydrogen atom spectrum. So I'm just giving you the gist of what I had written earlier, so you can see that. Okay. So if all the electrons came from any orbit but to the lowest orbit, 1, that you can see is the leftmost curve, And you can see in the bottom, it is the wavelength across. Therefore, energy is high on the left side because smaller wavelength means higher energy. So, the highest energy is the Lyman series of lines. And then if all the electrons came from whatever orbit, but they came down to orbit number 2, that was called the Balmer series. And then you can see another group of lines called the Lyman-Balmer. What's the next one? Paschen. Then bracket and then Fund and so on. So what Niels Bohr did was to give a quantitative theoretical picture of these transition frequencies, and earlier these transition frequencies were fitted to a constant called the Rydberg constant before Niels Bohr came. The Rydberg constant was a number, people all fixed, it's 109,677 centimeter inverse, a Rydberg constant. But what Niels Bohr did was to give precise statement on the basis of quantization of the angular momentum. He derived the formula and the formula was accurate. It fitted all the lines beautifully, but it fitted only for hydrogen atom. It didn't. When he tried to do this for helium or when he tried to do this for other atoms, there were problems. Also, if you put the hydrogen atom in a magnetic field or in an electric field particularly, there was a splitting of each of these lines into a doublet, 2 lines very close to each other. That was not there in the picture of Niels Bohr. So, it is like this, when you go and you try to look at the elephant, all of you are blind, you know the story. ஐந்து குருடர்களும் யானையும். ஓகே, படிச்சிருப்பீங்க எல்லாரும். ஒருத்தர் யானை கயிறு மாதிரி இருக்குன்னு சொல்றாரு, ஏன்னா அவர் வாழை தொட்டு பார்த்துட்டார். இன்னொருத்தர் யானையை மரமா இருக்குன்னு சொல்றாரு, ஏன்னா உடம்பை தொட்டு பார்த்தார், இல்ல காலை தொட்டு பார்த்தார் நினைக்கிறேன். இன்னொருத்தர் சோறு மாதிரி இருக்குங்கிறாரு, உடம்பை தொட்டு பார்த்துட்டேன். அப்புறம் காதை தொட்டு பார்த்துட்டு இன்னொருத்தர் வேற மாதிரி இருக்குங்கிறாரு. எல்லாத்தையும் சேர்த்து போடுறதால யானையுடைய பிக்சர் வரும். இந்த சேர்த்து போடுறது யார் போடுவாங்க? 2 people came later. All these independent thought processes were later brought into a unified viewpoint, and the first among these was Werner Heisenberg. Okay. Please remember, Heisenberg discovered all these things just about 3-4 years older than your age. Okay. Heisenberg discovered this around 20, when he was 24. Niels Bohr model, I'll leave all these things. And after Niels Bohr, there was Louis de Broglie. I just moved further, but I'll come back to him. But then you see Heisenberg and Schrödinger. So Werner called Heisenberg, 75 years he lived, 1901. He published his paper in 1925, so at the age of 24. I mean, Srinivasa Ramanujan had discovered many of these things from the age of 15 onwards. So, individuals who are very talented, we do not know how they get their talent, but they all have a way of finding out, solving problems which we never know. But we can learn from them how they did, and then how they pursued a problem to its last line. So that degree of vigor, or that's what makes the science very interesting. Okay. So Heisenberg was the student of Arnold Sommerfeld. Arnold Sommerfeld was the one who tried to expand the Bohr model into elliptical orbit model, 2 quantum numbers instead of 1 quantum number that Niels Bohr came up with. And Heisenberg was a young student of Sommerfeld. He did his PhD with him. And soon after that, he joined Max Born. I don't know, yeah, it's down there, Max Born. And Max Born was around 40, 42, and Heisenberg was around 24 when they wrote this famous paper together on the spectra of hydrogen atom from a new mechanics called matrix mechanics. Okay. Matrices were known at that time, and a lot of theories of matrices were proposed by David Hilbert. You can see that name there, David Hilbert. And he was a mathematician, very well known at the time. And Max Born knew that some of what Heisenberg was doing was very much the same as the matrices that Hilbert had used. So this whole process came up as a matrix mechanics, and in that process what he did was he put the momentum of the particle that he was studying, the hydrogen atom, the electron, and the position of the electron together. He assigned matrix to them, column vectors to them. And matrices don't commute. The product of two matrices A and B does not give you the same answer as the product of the matrices B and A. So this non-commutativity, they do not commute with each other. That was already known for matrices, and Heisenberg, because he associated the matrices with position and momentum, he found out that the product QP minus PQ satisfies the commutation relation IH bar, where I is a square root of minus 1. Two things at that point of time. One is operators. Why do we have to put matrices for Q and P? Nobody knew. Second, how come the complex number, imaginary number I square root of minus 1 slowly comes into this picture? That's a surprise. I mean, these things you will learn when you read more and more the historical background. And quite obviously, when this was published, mathematically it was one of the best presentations, and people believe that finally the mechanics, the quantum mechanics has been understood in the form of position, momentum of the particles and the commutation relations between them. And that principle is called the uncertainty principle. Also, what it essentially means is that for a particle, you cannot have both exact values for position and exact values for velocity of the particle at a given time, as we would imagine in Newton's law. Because when you shoot a target, you can calculate very precisely its position and its velocity using the Newton's laws. Therefore, the classical mechanics allows this precise property assignment. Quantum mechanics said the atoms do not have that property. At any given time, you either know the position extremely well, or you know the position extremely well in Q, either of this. But if you want to know both of them, there is error associated with each of them. The errors are such that the error in Q position and the error in momentum P at a given time, the product of that cannot be less than h bar by 2. That's the uncertainty principle. It is not that we cannot give you momentum and position. We can calculate, but we cannot give exact values. Approximate position and momentum for a particle we can always have. What is the approximation? It should be, the error should be greater than the product. Delta x, delta p should be greater than h bar by 2. Okay. If you thought all of this was good, then I needed to, okay, let me go back. There was always in the corner Professor Schrödinger, who was there in around that time. And Schrödinger was listening to these things and he was reading all these things. He was very unhappy about the way science was being done. Okay. He was not comfortable with Born's and Heisenberg's model. Schrödinger listened to de Broglie's lecture, Charles Louis de Broglie, you will see here. Louis de Broglie. Louis de Broglie is a French professor, and he started his life as a BA history candidate. He got his history degree. Then there was First World War. Please remember, he was born in 1892. The First World War began in 1914. So he was 22 years old when he entered. And France made every young person compulsory to participate in the war, to be a soldier, this kind of requirement. So he went into the war and he operated all the cannons and the, guns and other things. So he was so fascinated by physics, which calculated very precisely how to destroy targets, how to destroy land, pieces through shooting, and the Newton's laws and other things which were operative, the chemistry, physics behind all these things. He became so fascinated that after surviving the war, fortunately he did not die in the war, many scientists died because they all went into the field and many of them lost their lives. But de Broglie was lucky that he did not. He came back and then immediately he did a physics degree. And in 1924, he came up with this formula, beautiful formula, 1923 or 24, that a moving particle with the momentum p can always have an associated wavelength. And the wavelength lambda is given by this formula, h by p. If you look at it, the h keeps coming again and again. H was there, first introduced by Max Planck. H was there later by Einstein. H was there again by by Niels Bohr. H was again there in Sommerfeld's work. And then Max Born, IH bar. H bar is h by 2 pi, that's all. But it's still h. And then de Broglie has h by p. So now everybody realized that the h is a fundamental constant that was discovered first time by Planck. And you cannot create that kind of a constant from the existing constants. Mass of the electron, mass of the particle proton, the charge, etc. From all of those things you cannot construct h. So h was a fundamental particle, and the h by p tells you very clearly that the lambda is insignificant for you and me. You and I are about 50, 60 kilograms. And suppose we travel at the speed of something like 5 kilometers and a minute, if we run 4-5 kilometers a minute. You calculate your velocity, your momentum, per second, how much will be? Something like maybe you can walk 2 meters per second. Let's assume that. 1 meter, that's very fast. 1 meter, 2 meters per second if you walk. And you are a 70 kilogram person, then your momentum is 70 into 2. But kilogram meters per second. 140 kilogram meters per second. And if you divide h by that number, you find out that h was an extremely small number, 10 raised to minus 34, 6.6. So if you divide by that number, already you have 200 or something in the denominator, and so h by p will turn out to be how much? Extremely small, 10 to the minus 20. So there is no wavelength for you. If there is a wavelength, it is 10 raised to minus 34, 36 meters. Can't be measured. Therefore, we look like we are all rigid people. The atoms don't. The mass of the electron is 10 to the minus 30 kilograms. And therefore, if you divide the momentum of the electron, if you divide h by the momentum of the electron, the lambda wavelength comes into about angstrom, 10 raised to minus 8 centimeters. That's a significantly high wavelength, and it can be measured experimentally because the spacing between crystals, atoms in crystals, is of the order of angstrom. Therefore, if the electron has a wavelength, if it's moving very fast, if you put it through a crystal, if it is a wave, the crystal will diffract the electron, just like it diffracts light. So when de Broglie proposed that the particles have a wavelength when they move, given by this for non-relativistic velocities, given by this value, immediately people thought this can be experimentally verified. So two people, Davison and Germer, two people in 1927, they diffracted the electrons. they found out that the electron has wave-like properties. And the other interesting things outside of this is that de Broglie's thesis, PhD thesis, contained this. It was reviewed by Albert Einstein as the external examiner. Albert Einstein felt that this was a different idea. It needed to be looked at further. And he said it's a novel idea, it can be accepted for his thesis. So de Broglie got his PhD, approved by the most famous person who already had won the Nobel Prize. 1921, Albert Einstein had won the Nobel Prize and was known as the pioneering physicist from relativistic theory. After Newton, Albert Einstein was considered to be the greatest ever physicist in the world. So given that his acknowledgement that the thesis done by Charles de Broglie was right, and Davison and Germer showed experimentally that the electrons could be diffracted, de Broglie won the Nobel Prize in physics, 1929, I think, sometime around that. A physics graduate student, a history graduate student, okay? It only took him 10 years to do physics. But with all of this, Schrödinger was sitting around at that point. Schrödinger listened to de Broglie and felt that the Max Born and Werner Heisenberg's model does not have any physical picture. Schrödinger said everything should be wave-like. The electrons of the hydrogen should be also wave-like. The particles, atomic particles, should all have wave-like properties. So which we call as a matter wave. Matter being something that is very precise, that is localized. Wave is something which is very imprecise and very delocalized, uniformly delocalized. So the matter wave is a connection of the localization and delocalization, how they exist together. Everything so far is physics, okay, and mathematics. So then Schrödinger came up and said, no, for hydrogen atom, I don't think that this model is the right, this approach is the right approach. So Schrödinger came up with his famous equation. I don't know if I have that here. I'm sure I have it. Okay, so I moved to Schrödinger's famous picture, obviously, was the equation that he had. Where am I? So tell me journal. Where is the journal here? No. Sorry. How do I get to journal? Oh, somewhere along I need. Okay, what do I do? How do I close this? Okay, thing is terrible. I look for journal to be. Can I annotate? I cannot annotate here. Never mind. I thought I would write the equation here, but looks like journal No, it should be here. Journaling. No, journal. Thank you. Okay. Yeah. So Schrödinger came up with a slightly different model for the hydrogen atom. What he did was he wrote down the equation again. This setting is not. I hate this. No, but the pressure set is not correct. Something is wrong with this. You guys have to set this up carefully, okay? Okay. So, Schrodinger's equation, see, it's also, my hand sensitivity is also there. That's the reason why I cannot put my hand and write. Yeah, please pick this up and do it. Okay, so while this is going on, I'll anyway carry on with this because the introduction to quantum chemistry just began. We are about running out of time. Schrodinger came up with his, what we call as the wave equation. And he proposed to the wave equation from the classical wave equation, which was known for many years. For hundreds of years, people have studied that in physics. He believed that associating waves with the motions and of the atoms and molecules was more physical and more visualizable. But Schrodinger also got into trouble in a way that his wave equation ended up with a complex number, the imaginary number I. Okay. So if I have to say, my sensitivity is less now? Sensitivity is less now? Okay. You have done something. Things just don't work for me because I introduced WACOM in 2005 to the whole education system in this country. Not WACOM, but tablets like this. You don't work. One of them should access. Okay. If simultaneously when you are doing that, this is a problem. Now I cannot get my pen. Okay. Thank you. You write what I say. I think it works for you. I h by 2 pi. Right? No, it doesn't work. Okay. Yeah, it's fine. I'm going to give this lecture again over the Zoom for you sometime. Okay. Yeah. No, they didn't set this up properly. That's all. Let me see. Anything at all can be done. The fact that I cannot write the Schrodinger equation is terrible. You don't even have a board, right? Yeah. Okay, never mind. This is. Do you have the internet? You have the internet? Try பண்ணு. Okay. Okay, leave that. Yeah, that's fine. I'll do this. Okay, say they finally allow me to write the Schrodinger equation. It's a dishonor if I cannot do that. Where is the eraser? Eraser is this? This one?
Eraser.
Eraser. Oh, okay, so I'll erase that. Fine, yeah, okay. Now I need to go to the pen, right? Right. Okay. D by dt is equal to, no, I should write at least this equation, no matter what it is. I'm not going to give up. Okay, I'm not going to give up on this. So it is minus h bar square by 2. Do you remember this equation by any chance? 2m e dou square by, you remember this? PPT, where is PPT? Yeah, I don't give up. Dou square by dou x square plus dou square by dou y square plus by dou z square. This is the operator, okay? But the operator acts on a function called the wave function, and this is one-dimensional Schrodinger equation. This is one-dimensional Schrodinger equation. Okay, I'm successful for today's lecture. I could write this. But what is important is, there is this I h bar d psi by dt is equal to h psi. Okay? There is something missing in this. What is missing? Plus V. So that this whole thing is a quantity called, there is a name for this quantity. There is a name for this quantity. What's the name, you remember? It's called Hamiltonian. Okay? Hamiltonian is not quantum mechanical. Hamiltonian is the general name, is a name given for the total energy of a system. It was Sir William Rowan Hamilton in 1850s, 200 years ago now. He described classical mechanics using a method called the Hamiltonian mechanics, in which the Hamiltonian was introduced as the operator, as the total energy. And before that, there was Newtonian mechanics, and between Newtonian and Hamiltonian, there was something called the Lagrangian mechanics. The Lagrangian was the difference between kinetic energy and the potential energy of a system. The Hamiltonian is the sum of the kinetic energy and the potential energy of the system. What Schrodinger did was, when he wrote down this equation, again, there was a problem of what is psi. Is there a meaning for psi, the wave function psi, other than saying that it is a mathematical function? Because he was worried that the mathematics of Born and Heisenberg is not very physical, but then you get a complex number. You also get into unphysical pictures. So what's the complaint? I mean, if you complain something is bad and you get something equally bad and you don't know how to explain the wave function. So Schrodinger had difficulty getting the exact interpretation for wave function. And you know who solved that problem? Born on the other side, whom he said was not very meaningful. Born came up with the correct interpretation for the wave function. He said it's not the wave function which is important, which has a meaning. It's the absolute square of the wave function, because it's a complex function. So you product complex function and its complex conjugate. Any complex number conjugated with its complex conjugate gives you a real number. Therefore, psi star gives you what is called the probability density, which describes finding the particles in time, in space. So Schrodinger, much as he was uncomfortable with Born and Heisenberg, it was Born who eventually gave the correct interpretation for the wave function. And today we study both the mechanics, both in science and chemistry, physics and chemistry. So let me do one thing. This is a starting point I want to leave, and I'll find some time maybe today, a little later, and carry on to say where the chemistry of all of these things map into where the chemical systems, and how chemistry later took control of this equation completely, Today, computational chemistry is orders of magnitude more advanced than computational physics. They started with Schrodinger equation, they started with Max Born's Heisenberg's equation, and then with the development of computers in the 60s and 70s, and with the development of the very large systems integration, VLSI, circuits and chipsets, prior to that the transistor. With all of that, and programming, Unix and others, chemists really brought the computational tools to modern level that today you can synthesize mentally a drug through computational means. And then you can verify whether the drug will have a chemical synthetic route and so on. So that many companies, pharmaceutical companies, use computational chemistry as a very important input instead of doing 10,000 laboratory experiments, which will be a waste of time and waste of resources and energy. So things have moved from 1926 to 2025, 99 years now. Things have moved to the point that today computational and theoretical chemistry, largely this part of theoretical chemistry is the ruler of the roost. Now, it's really one of the most important requirements for all of chemistry. I'll stop here. My colleague has arrived. Where is he? Where is he? Ask him to come. Professor Rajkumar will continue with chemical kinetics and atmospheric chemistry and others. I'll see if I have some time later. And if not, I'm going to probably give a series of lectures over the internet on Zoom, preferably on specific Saturdays and times. I'll inform all of you. This group will be a WhatsApp group. I'll inform Professor Devasenapati so that you can come online and probably listen to about half an hour, 45 minutes.